Hello everyone. The topic for this lecture is certificate revocation, and we will focus on two methods of how certificate validity information can be distributed to relying parties. In particular, CRL, which stands for Certificate Revocation List, and OCSP, which stands for Online Certificate Status Protocol. Let's begin. So, when a certificate is issued, its validity period is limited by the validity date set in the certificate. Remember these not before and not after fields. The reason why there is this validity period is similar to why identity documents such as passports have it. The technology, for example, the security features used in the document can become outdated, and the same is true for certificates. Over time, the cryptographic algorithms can become weak. Therefore, it is a good idea to limit the validity period of the certificate. So, the validity period limits the time period for which the certificate can be used. In practice, however, this is not enough, since it may be required to invalidate or revoke a certificate before its expiration. Some examples. If it turns out that the private key is compromised or lost, we would want to revoke the certificate so that relying parties would stop trusting it, right? Then it can turn out that the certificate has been misissued. That is, it turns out that some wrong data has been included in the certificate, and therefore it should not be trusted. Another reason is if the data has changed, meaning that the information specified in the certificate does not represent the current situation anymore. For instance, if the name of the person or the affiliation of the subject specified in the certificate has changed. So, the question is how to distribute the information about revoked certificates to relying parties. And the trivial solution here is the so-called certificate revocation list. So, what is it? It is a list of unexpired certificates that have been revoked by the CA. So, it is a blacklist of revoked certificates. Expired certificates are removed from the list because once they expire, they are considered invalid anyway, right? But there are several practical questions that we have to solve for the system to work flawlessly. Namely, where can a relying party find the CRL? How can we assure the integrity of the CRL? How frequently should the CA issue or update the CRL? How frequently should the relying parties refresh the CRL? And how can the relying party verify that the CRL is fresh, meaning that it is the most recent blacklist? Let's try to answer these questions one by one. The link where the CRL is available is specified in the subject certificate in the CRL Distribution Points extension. Here is the example of the facebook.com certificate. So here we see a link to some file that has the CRL extension. This file is hosted on two web servers to provide better redundancy. The data in the CRL, surprise, surprise, is encoded using ASN1 Duran coding. Let's see what is inside. So there is a sequence containing three elements: the to-be-signed certificate list, signature algorithm used to create the signature, and the signature itself encoded as a bitstring. The CRL is signed by the same CA that issued the certificate whose validity we want to verify. So this is how the CA provides integrity for the data in the CRL. The certificate list here is a sequence which contains a version number, by default version 2, signature algorithm the same as here, and issuer distinguished name, which should be the same as the issuer name in the certificate we want to check. Now, these two fields are very important timestamp fields. The this update field specifies when the CA produced the CRL, and the next update field specifies when the CA commits to publish a newer, more recent CRL. So, to verify that the CRL is the latest available CRL, the current time should be earlier than the date specified in the next update field. Usually, CAs update the CRL twice a day, or at least once in a few days. Then comes the list of revoked certificates. This list actually contains only the serial numbers of the revoked certificates. Since the serial number is unique, it uniquely identifies the revoked certificate. Then there is also the time when the certificate was revoked and some optional extensions, for example, providing a reason code for why the certificate was revoked. Then there can also be CRL extensions, which provide more information about the particular CRL. For example, whether the CRL contains all the revoked certificates issued by the CA or only certificates issued to end users, or whether it includes all the revoked certificates or only the certificates revoked for a specific reason. So this data structure allows a relying party to check that the CRL is authentic and fresh and check whether the certificate is not revoked. If the certificate has not expired and is not in this list here, the relying party can assume that the certificate is valid. Okay? Here is a summary of what we discussed on the previous slide. Now, to check if the certificate is valid, we have to check not only the subject certificate, but also the validity status of all the certificates, including the CA certificates in the certificate chain. So here is a certificate chain. How would we validate it? How to validate a certificate chain? First, where to check whether the subject certificate is not revoked? Well, in the CRL issued by the intermediate CA. So here in the subject certificate will be a link to the CRL signed by this intermediate CA which issued the certificate. Usually these CRLs are updated every 12 hours. So as you see, a situation can occur where a certificate is revoked, but the CRL where this certificate will be listed is not yet issued. So there is some period of uncertainty for the relying party until a newer CRL is issued. And this period is called a grace period. Now, a question to you. What should the relying party do in this grace period? Should it assume that the certificate is valid? Or should it postpone the operation until a newer CRL is issued and the relying party can ensure that at the time the certificate is received, it was valid? Here it is up to the relying party to decide whether to risk and consider the certificate valid or to wait until a newer CRL is issued. Now, where to check whether the intermediate CA certificate is not revoked? In the CRL issued by the root CA. So, in the CRL specified in this certificate, which will be signed by the root CA. Root CA usually update their CRLs every 3 months or so, because the root CA private key is offline, and therefore signing something with the root CA private key is a manual operation. Now, what is a grace period here? Will we wait for 3 months to figure out if the intermediate CA is not revoked? Probably not. Therefore, in practice, the validity status of intermediate CAs is not checked. It is presumed that the certificate is valid. Now, where to check whether the root CA certificate is not revoked? Well, in the CRL issued by the root CA itself, meaning that the root CA revokes itself. This is, however, a flawed solution, because if the CA private key is compromised, the attacker can issue a self-signed CRL which will not list the revoked CA certificate, right? So the only meaningful way to revoke a root CA is by some out-of-band means, for example, through a software update. And intermediate CA certificates are also usually revoked through a software update. Now, a hypothetical question to you. Who should be liable for the actions made after the root CA private key has been compromised? For example, a fraudulent certificate is issued and a forged transaction is made with it. Now, who should take the responsibility for this forged transaction? I think it would be reasonable to say that before the CA informs the relying parties, the CA should be liable. After the relying parties have been informed, the risk of accepting the transactions should fall on the relying parties. So there has to be some channel to announce to all relying parties that the root certificate should not be considered valid, right? In practice, it would be the same channel that was used by the relying parties to learn that the root CA can be trusted. For example, browser's trust store. It is hard to say what would happen in practice, as there have not been too many root CAs whose private keys would have been compromised. Anyhow, let's analyze these type of liability issues a bit further. PKI is a nice technology, but it cannot function successfully without some legal framework. It should be clear to everyone who is liable for what and who takes the financial risks if something goes wrong. So let's assume a real-world situation where a subject's private key has been compromised. Meaning that somehow an attacker has obtained the private key, and this now allows the attacker to impersonate the subject, engaging on behalf of the subject in some financial transactions that are, let's say, worth millions. Now, let's try to answer who, the subject, the CA, or the relying party, should take liability for the actions made with the compromised key. By liable here, we mean who will cover the financial loss caused by the fraudulent transactions made with the compromised private key. Of course, it is the attacker who should be held liable, but let's assume that we don't have the attacker here. We don't know who the attacker is. So there are three parties involved in the PKI who potentially could be held liable: the subject, the CA, or the relying parties themselves. Now I will ask a list of questions. Try to pause the video to think through and come up with your own answer before I provide mine. So, who should cover the losses if the fraudulent transaction has been made in the time period after the revocation information of the compromised key has been published in the CRL? I think we can agree that the relying party is at fault, because the relying party did not care to check the CRL where it was announced that the certificate should not be trusted. Now let's modify the situation a bit. What if it happened in the time period after the CRL has been issued but is not available to the relying parties? For example, due to the CA server being down for maintenance. I would say that it's still the relying party, because it went on with the transaction without gaining the assurance that at the time of transaction the certificate was still valid. Now, on the other hand, it was the CA's responsibility to make the CRL public. So here the relying party could ask for some compensation for the downtime, but this depends on the agreement between the CA and the relying parties. However, the relying party cannot ask the CA to compensate for the losses caused by the fraudulent transaction. I hope that it makes sense. What about the case when the fraudulent transaction is made in the time period before the next CRL has been issued? So the certificate was revoked at the time of the transaction, but the CRL, which would list it, was not yet issued. Still, the relying party should be liable because it did not verify whether the certificate was not revoked. Well, you could say that it had no technical means, and that is true, but it knew that there is some uncertainty for accepting the certificate in this grace period, but it still decided to accept the risk, right? What about the time period after the CA has been informed that the key should be revoked, but before the CA has marked the certificate revoked in their database? Here we have to define what constitutes the moment at which the certificate is revoked. Is it the point when the subject informs the CA, or is it the point when the CA makes the decision and registers revocation in their system? You might be surprised, but the law does not provide a clear answer to this question. According to the EIDAS regulation, the CA has to make the decision about the revocation in 24 hours. The law does not say who is liable for the fraudulent transactions made in this period. I haven't heard about court cases where this question would have been dealt with, so we can only speculate here. Now, what about the time period before the CA has been informed about the key compromise? We could say that the subject should cover the losses because it was their duty to protect their private key and inform the CA in case of compromise. But what if the subject did not know that their private key has been compromised? Is it fair for the subject to cover all the losses? We will look at this question in the next lecture when we will study digital signatures and their legal power. But the point here is that PKI deployments require much more than the technology. Without being able to answer these type of legal questions, we cannot be sure that the security system we have built will achieve the required business goals in case something goes wrong. So it seems so far that PKI works fine, but maybe it seems so only because most of the important transactions are still being made offline without relying on the PKI. So we have not really tested who would eat the losses if something goes terribly wrong. All right, we are done with the CRL topic. You should now be able to answer these questions. Now let's talk about the CRL successor, which is called Online Certificate Status Protocol. The main CRL shortcomings are the size of the CRL, because CRLs can grow very large. For example, after the flaw in the Estonian ID card was found in 2017, more than 1 million certificates had to be revoked. The result was that CRLs grew to more than 100 megabytes in size. So, as you may guess, downloading this data frequently is quite expensive. Then there is the client-side complexity in parsing the CRL. The problem is that the relying party has to go through all the entries in the CRL to ensure that the serial number is not among them. The serial numbers in a CRL are not sorted, so the verifier has to do a sequential scan over all the entries in the CRL. Then the most important problem is that CRLs contain outdated status information, as they are not updated instantly. The solution here is the Online Certificate Status Protocol, OCSP, which enables applications to determine the state of a particular certificate. Since this is an online protocol, it can provide real-time information about the certificate. Here we don't have to download the whole blacklist. We can ask for validity information about a particular certificate of interest. A few questions we have to answer. First, where can the relying parties find the OCSP responder? How is a certificate identified in the OCSP request? How is the integrity of an OCSP response assured? And how can the freshness of an OCSP response be ensured? So let's discuss these questions one by one. So the URL of the OCSP service is specified in the certificate's Authority Information Access extension. Here is the example of the facebook.com certificate. So this URL here is the URL of the OCSP responder of the CA DigiCert that issued the certificate. As you see, the OCSP service works over the HTTP protocol. To see exactly how the protocol looks, we can use the tool Wireshark. We can use Wireshark to sniff the communication between our browser and the OCSP server. This is how it looks when we open Wireshark. Here it shows the network interfaces that we have. Here we select our wired network interface, and here we can enter a capture filter to sniff only those packets that are sent to the OCSP server. So here we write host OCSP-digicert.com and click here on this button to start capturing the packets. Now we can open Firefox and connect to facebook.com, and we will immediately see that an OCSP request is made to check the validity of the facebook.com certificate. We can right-click on any packet belonging to this connection, follow TCP stream, and we will see the bytes that are sent to and from the server. The red here is the request sent by the client. The blue is the response from the server. As you see, here is some HTTP header, then some binary blob, HTTP response header, and some response blob. These binary blobs are, surprise, surprise, ASN1 encoded data structures. The client sends some request, and the server responds with some structure. Let's look at the request. What we see here is a to-be-signed request, which optionally can be signed. Usually OCSP servers accept anonymous requests, so there is no need to sign them. But signing is supported and may be useful if the OCSP service wants to accept only authorized requests. So in case the request is signed, the field contains signature algorithm, signature, and optionally the signer's certificate chain. The request itself contains version, optional a distinguished name of the requester, and the list of certificates in whose validity status we are interested. The certificate is identified by the issuer's name, issuer's key, and the certificate serial number. So why is the certificate serial number not enough? This is because one OCSP service can provide information for several CAs. Hence, we have to identify not just the serial number, but also the CA who issued the certificate. To save space, the issuer's name and the public key is hashed using the hash algorithm specified in this field. The response is a sequence with two entries: response status, which contains whether the request has been successfully processed, and the response bytes that contain the actual response. Response status defines several error cases. If the status is successful, it will contain the code 0. Response bytes specifies the type of the response, usually corresponds to OCSP basic, and the response encoded as an octet string. Note that the response bytes field will be provided only if the response status field is successful. So this code here is 0. The response data structure is a sequence containing to be signed response data, signature algorithm, the signature itself, and optionally the certificate chain of the party who signed the response. The signed response contains the version number, the distinguished name of the responder, the produced at field that specifies the time when the OCSP service signed the response, and then for each requested certificate there will be a corresponding response. Cert ID identifies the certificate, and cert status contains the validity status. The cert status field can contain 3 values: good if the certificate is valid, revoked if it is revoked with the revocation time and reason, and unknown if the OCSP responder does not know about such a certificate. For example, if it is asked to provide information for a certificate that the CA has not issued. Now, every response entry will also have the this update and next update fields similar to CRLs. The idea is that the OCSP service can work on CRL data, but usually it has direct access to the CA database and can provide real-time status information. If it provides real-time information, then the this update and next update fields will be set to the current time. The produced at time here will also contain the current time, specifying the time when the OCSP service signed the response. Okay? Now, let's answer the question, who signs OCSP responses? And here are several options. The standard says that the key used to sign the response must belong to one of the following. First, it can be the CA who issued the certificate in question. This is the same as in the case of CRLs. This approach, however, is very rarely practiced. You really don't want to connect a CA private key to an online service that has to parse untrusted data received over the internet. In such a case, if an attacker was able to compromise the OCSP service, the attacker would be able to forge signatures with the CA private key, for example, issue certificates, which is not good at all. Therefore, usually OCSP responses are signed by a CA authorized responder who holds a specifically marked certificate issued directly by the CA, indicating that the responder may issue OCSP responses for that CA. This way, the CA can delegate OCSP signing to another party. Technically, this OCSP signing delegation is designated by the inclusion of the OCSP signing flag in the extended key usage extension of the responder certificate. This way, if this key gets compromised, an attacker can forge only OCSP responses in the name of the CA, but cannot issue certificates in the name of the CA, right? But now the question is, how can the revocation status of this certificate can be checked? And the answer is that it is not possible. We have to trust that certificate. Usually, the certificates are valid only for a few days. They are frequently rotated so that the harm done in case of a compromise is limited. Then there is an option that OCSP responses can be signed by some trusted responder whose public key is trusted by the requester. In such a case, we cannot rely on the PKI. Hence, the trust must be established by some out-of-band means. This option is usually used only in closed environments where the OCSP responder is manually configured to explicitly trust some responder. Now, how can the freshness of a response be checked? The problem here is a replay attack. The idea of the replay attack is that the attacker can perform a man-in-the-middle attack on our connection to the OCSP server and replay some valid, outdated response, which is obtained when the certificate is valid, while the certificate is actually revoked and should not be trusted. To prevent replay attacks, we can check the signed produced at field to see when the server issued the response. But what should be the allowed time difference between the current time and the time specified in this field? Most likely it will not be the current time because it will take some time for the server to sign the request and transmit the response back to the client. So how large of a time difference should be tolerated? 2 seconds, 5 seconds, a minute? To enforce this freshness check, we also have to rely on the correctness of the system clock. If we don't have access to a trusted and precise system clock, this check becomes problematic, right? An alternative way to check the freshness of an OCSP response without the need to rely on the time is to include a random nonce in the OCSP request and check it in the response. So there is an optional OCSP nonce extension. By using this feature, the client can verify that the response was produced specifically for the client, as the signed response will contain the nonce that was specified in the request. This prevents replay attacks. Why? Because the attacker cannot predict what nonce value the client will send. The attacker cannot collect valid OCSP responses for all the possible nonce values the client may send in the future. So, if we use the nonce extension, we don't need to rely on the correctness of the system clock, but we need to have a decent enough source of randomness, right? Now the problem with this extension is that it is not mandatory for the server to support this extension, and it makes this mechanism vulnerable to so-called downgrade attacks. For example, if a client sends a nonce in the request but gets back a response without the nonce extension, there is no way to distinguish whether it is a replay attack or this is a legitimate response from an OCSP service which simply does not support the nonce extension. The client can detect this downgrade attack only if it somehow knows that the server supports the extension. So a downgrade attack becomes possible whenever there is an optional security feature, but there is no secure way of distributing the information about whether it is supported by the parties. In this case, the attacker can simply strip off the security feature without this being detected. A smart way in which it could be solved for the OCSP protocol would be to include some flag in each signed OCSP response, which would signal to the client that the server supports the nonce extension. Then, if the client sees this flag, but there is no nonce extension in the response, the downgrade attack can be detected. Now, a much bigger problem with the freshness checks in practice is that WebPKI allows OCSP servers to implement OCSP response caching, returning cached or pre-generated responses. Now, think about the OCSP server which provides validity status for Facebook.com. It may be computationally too expensive to sign an OCSP response for every user who tries to connect to Facebook.com. The OCSP server will pre-generate OCSP responses, distribute them over a content delivery network, and perhaps update them only once per few hours. In this case, the best freshness check that can be done is to verify that the current time is between this update and next update field specified in the OCSP response. However, in such cases, the real-time validity status cannot be obtained, and we end up having a grace period the same as when using a certificate revocation list. Let's look at how revocation checking is handled by browsers. If you're wondering, CRLs are not supported. A long time ago, Firefox had an option to manually configure and load CRLs, but apparently nobody used that feature and it was removed. OCSP is supported by browsers, but there are several problems with online OCSP checks. First, there is a privacy leakage, because by sending an OCSP request, the OCSP server and anyone who is sniffing the connection to the OCSP server learns what websites the user is browsing. The OCSP server sees the IP address and from the certificate which is validated can find the domain name that the user is accessing. Another problem is that it makes initial page loading slower. The browser has to contact the OCSP server and verify that the certificate is valid before the connection to a web server can be fully established. So here the speed of page loading depends on how fast the OCSP responder can send back the response. If the OCSP server is down for maintenance, then effectively we will not be able to open the website. For this reason, OCSP checks are not generally performed by the Google Chrome browser. Generally because on the Windows and macOS platforms, Chrome uses operating system crypto libraries which may perform OCSP checks. As the main revocation mechanism, browsers rely on a blacklist distributed using browser updates, so-called CRL sets in Chrome and one CRL in Firefox. These lists contain revoked CI certificates and some high-impact end entity certificates. So this mechanism works well to revoke root CI certificates, but is not able to revoke all revoked end-user certificates. In addition to this mechanism, Mozilla Firefox performs OCSP checks for end entity certificates. To check CI certificates, OCSP is not used. The problem, however, is that even though Firefox uses OCSP, Firefox is not brave enough to fail-safe or hard fail. What it means is that if we take a look at the OCSP configuration parameters in Firefox, we will see that OCSP here is enabled, but the OCSP require option here is set to false. What it means is that Firefox will try to contact the OCSP server, but if the OCSP server does not provide an answer in 2 seconds, it will give up and continue loading the page assuming that the certificate is valid. This means that a man-in-the-middle attacker can simply block the OCSP request made by the browser, and the browser will assume that the certificate is valid. What it means in practice is that the attacker who has compromised the server's private key can perform successful man-in-the-middle attacks even after the certificate is revoked, because the attacker can block the connection to the OCSP server so that the browser never learns that the certificate has been revoked. So here is a big question of whether such software OCSP checking provides any security benefit at all. If you want to force the browser to perform a successful OCSP check, you can set this parameter to true. A few years ago, I tried browsing the internet with this set to true, but soon after I hit a website which I could not open because the OCSP server was down, and after that I gave up and disabled it. Data from Mozilla's telemetry project indicates that over 7% of OCSP checks actually time out. So, as you may guess, Firefox users would be angry if this option was set to true. Therefore, to not lose users, Firefox has not enabled this option by default. A solution to this problem is the so-called OCSP stapling. The idea here is that instead of each browser contacting the OCSP server, the web server obtains a valid OCSP response and provides it to the browser. So when the browser connects to the server will provide not only its certificate, but also a fresh OCSP response. This way, it becomes the server's duty to regularly contact the OCSP server and obtain fresh OCSP responses. And this solves several problems. There is no privacy leakage because the client never contacts the OCSP server directly, and it also saves bandwidth because only the web server contacts the OCSP server and not the million clients who are connecting to the web server. This mechanism has been standardized and is supported by all web browsers. So if Firefox receives a valid OCSP response from a web server, it will not contact the OCSP server. But we still have the problem of the downgrade attack, because the attacker can pretend that the server does not support OCSP stapling, right? To solve this problem, the OCSP must staple certificate extension can be used to prevent downgrade attacks. So when applying for a certificate, the subject can ask a CA to include this extension in the server certificate. In case the browser receives a server certificate that has this must staple extension, but the server does not provide an OCSP response, the browser will hard fail by refusing to connect to the server. Today, Firefox supports this extension, but Chrome unfortunately ignores it. Then the question is, how fresh should the OCSP response be? The answer is 10 days. So here the browser and CA community has agreed that OCSP servers must not issue OCSP responses that are valid for more than 10 days, meaning that the difference between this update and next update should not exceed 10 days. As you may guess, the bigger the difference, the larger the time window in which a revoked certificate could be used in man-in-the-middle attacks. Another idea how to tackle this revocation problem is to issue certificates with a shorter certificate validity period. For example, the CA Let's Encrypt issues certificates that are valid only 3 months. This way, if the certificate gets compromised, the time window in which it can be exploited becomes smaller. Browser vendors are moving to enforce shorter certificate validity periods. Currently, server certificates must not be issued with a validity period that is longer than 1 year and a month, and it is likely that the validity periods of server certificates will shorten even more. Anyhow, the entire message here is that revocation checking by browsers is not perfect, and if you have a high-impact certificate that has been compromised, the best course of action would be to contact browser vendors directly so that your compromised certificate could be blocked through browser updates. All right, very good. Now you should have answers to these questions as well. Let's look at how HTTP or Hypertext Transfer Protocol works. This will be needed to implement the homework task. So HTTP is an application layer client-server request response protocol, meaning that a client sends a request and the server responds. So request, response, request, response. HTTP runs over TCP port 80. The TCP protocol is a protocol that can be used to establish a connection to some server, to a specific port, and then to transmit and receive bytes. The port number is like a service identifier. Different services can be run on different ports. The standard port for plaintext web services is port 80. So how does a client request look? For instance, if we want to request this URL, example.com/hello, we will have to connect to TCP port 80 to the IP address which corresponds to the example.com domain name, and then we will send some bytes. Our request will have a header where we specify the HTTP request method GET, the path which we want to request, and HTTP version 1.1. Then we specify the host name to which the request should be sent, because one IP address can host several websites with different domain names. Then we can send other headers. For example, connection close. This will signal to the server that it can close the TCP connection after serving us the response. We use GET requests when we want to receive some data, and POST requests when we want to send some data to the server in our request. For example, here is a POST request where we want to send 24 bytes. The header will end with an empty line, after which we send our 20 data bytes. If you count, you will see that this string is 24 bytes long. So for POST requests, we have to specify this content length header so that the server knows when it has received the full request body. The TCP protocol does not have any way to signal to the other party that we have sent all the data that we intended. So the number of bytes that you want to send has to be signaled to the other party on the application layer, HTTP in this case. So in a GET request, the server will wait until their headers are received, but in a POST request, we'll wait until the full POST request body is received, and only then will provide the response. The TCP protocol is asynchronous, meaning that both parties can send the data at the same time. For example, based on the request header, the server can conclude that it is not interested in the data we plan to send and can return the response before receiving the complete request body. This is an example of a typical response. The first line is the status line. Code 200 means OK, the request was processed successfully, and there will be some headers. Date, server version, content type, and the content length header, which tells us how many bytes in the server will return. So after the header, there is an empty line, and here comes the 7,000 bytes in the response body. So the header lines for the request and response must all end with two new line characters, CR carriage return and LF line feed. This is how we can define these byte values in Python. Header lines are separated from the body with an empty line, and post requests will have a non-empty request body. If this did not make sense, read more about HTTP on Wikipedia. Now, to send some bytes over a TCP connection, we have to use sockets in Python. This is how it works. We import the socket module. This is how we can create a TCP/IP socket with some flags, not important. Then we use the connect method on this socket to establish a TCP connection to this host on port 80. We can specify here a hostname or an IP address, both will work. Once the connection is established, we can send some bytes over the socket using the send method, passing the byte string we want to send. So this is a complete HTTP request, and the send method returns integer 37, which is the number of bytes that were successfully sent to the remote host. If you count, you will see that this byte string contains 37 bytes. Now, to read back some bytes, we can call the receive method, specifying how many bytes we are expecting. Here we specify 20, and these are the 20 bytes, the beginning of the HTTP response header. What is important to understand is that the receive method returns bytes that are available in the read buffer up to the number of bytes specified, but it can as well return less. The receive method will wait if the read buffer is empty, so this call will block until something is received from the peer and is pushed into the read buffer. The receive method will return 0 bytes if the connection is closed. So if the response is empty, you can safely destroy this socket, as you will not be able to send or receive anything on it. As you see, we must know how many bytes we must get. This information has to be inferred somehow from the application protocol. In HTTP, we know that when we get an empty line, we have received the full HTTP header, and we can use the content length header to figure out how many bytes to expect in the HTTP body. To summarize, the correct way to read HTTP response is to read byte by byte until the full response header is received. That is, when we get an empty line, then we can read actually more than 1 byte at a time, but then we must check that the receive method returned the amount we requested. Remember, receive method returns bytes that are available in the read buffer. It is not guaranteed that it will return the number of bytes we requested. Okay? Then extract the body size from the content length header, read byte by byte until the full response body is received, and avoid endless loops by checking the return value of receive. If it is empty, the connection is broken. Here you can read more about sockets in Python, but this slide should provide enough information to implement the homework. So the homework task is to implement an OCSP checker. Implement a utility that queries an OCSP responder for a certificate's validity. OCSP check.py, which takes a single argument of the certificate to check. The utility will extract the URL of the OCSP responder from the certificate from the Authority Information Access extension. In the same extension, find the URL of the issuer certificate and download the certificate. It will construct the OCSP request for this certificate and print out the serial number. It will connect to the OCSP responder, send the request, read back the response, and print out produced at, this update, next update, and the certificate status. There are two certificates in the course repository, valid.pem and revoke.pem for a revoked certificate. Okay. Some notes. The code has to extract the OCSP responder's URL and CI certificate's URL from the certificate's authority information access extension. Send HTTP request using Python sockets the correct way, which was explained on slide 20. The purpose of this homework is to learn how to correctly send and receive bytes using sockets. We will also use sockets in future homework tasks, therefore make sure to get it right. Check whether the connection is not broken and make sure that the expected amount of data is received. The solution will be penalized if these checks are missing. Use the URL parse module for easy URL parsing. Import URL parse. Then you can use the URL parse method, passing some URL, and you will get back a parse result object where you can access host, path, and other fields separately. For example, to get hostname, use netlog attribute. You can use irregular expression to extract the length of an HTTP response body. If you have not mastered regular expressions yet, it is a pretty powerful way to perform pattern matching to extract substrings from a text. Import the regular expressions module, and you can use this regular expression, which will search for this pattern in the header byte string. What it will look for is the string content length, followed by 0 or more whitespace characters, then 1 or more digits, and again a whitespace character. The I flag means that this search will be case insensitive and will also match the case where content length will start with a capital letter. The S flag will interpret the text in the header as a single line. This group 1 will return the contents in these parentheses, these digits here. Note that this result will be a string, so you have to cast it to an integer to use it later. Okay? Construct the OCSP request using your ASN1 encoder. To construct issuer key hash for cert ID, encode subject public key bits to bytes. Take bits from the subject public key, convert them to bytes, and hash these bytes. To make your life easier, a full implementation of the OCSP response parsing code is in the template. Signature verification checks can be skipped. In practice, you would have to verify not only the signature, but also check if the key used to sign the OCSP response is authorized to sign OCSP responses, and so on. This we will skip because that would be too complicated for this homework. Some additional notes. OCSP requests must include the content type application OCSP request HTTP header. Otherwise, the request may be rejected by the server. Some web servers require this header, some don't, but it is better to include it. To debug HTTP errors, use Wireshark's follow TCP stream feature. If you get an HTTP error from the server, the problem is not in your OCSP request, but in your HTTP request. Use this feature to verify that what you think is sent to the server is actually the bytes that are sent to the server. Note that an OCSP responder may return unauthorized for unrecognized cert IDs. This will happen if the OCSP server has access only to pre-generated OCSP responses. In this case, the server does not have access to the OCSP signing key, and therefore it cannot return a signed OCSP response containing the status unknown. Therefore, as a workaround, if it receives a request for a certificate for which it does not have a pre-generated response, it simply returns an error code. So if you get this response, make sure that your cert ID in the OCSP request is constructed correctly and that the certificate you're checking has not expired. This is how an OCSP request for valid.pem should look. If you get here something different, your structure is incorrect. Final comments. To emphasize once more, the wrong way of downloading HTTP request body is reading the response in one go. For example, if you have this line which asks for content length bytes, it is not guaranteed that it will return all the content length bytes in one go. This is because the receive calls normally return any data available up to the requested amount, rather than waiting for receipt of the full amount requested. Keep this in mind. Another wrong way is reading until the socket is closed. For example, this code which reads whatever is sent until the connection is closed and the receive method returns an empty string. The problem here is that after sending a response, an HTTP version 1.1 server will wait for more request-response exchanges unless the header connection clause was specified by the client. This means that using this approach, the receive method will hang until the timeout configured by the server is reached and the server closes the connection. Don't do this. Read until you get the amount that is expected and then close the connection. Okay? Alright, that is it for the homework. Good luck with implementing it.